Hello and welcome to this podcast on how new tech is going to impact military aviation. I am M. Marshall Mohan. Disruption by technology is not new. We have constantly been subjected to it. However, the pace of disruption due to what we call Industry 4.0 technology is rapid and far-reaching. Humans, with our inherited genetics, can be expected to first apply these technologies to war. We usually make the mistake that the nature of warfare is relatively static and technology only refines or improves the instruments of war. Industry 4.0 technologies will not just improve the instruments of war, but change the very nature of war itself. Even preceding the arrival of these technologies, many new facets of warfare, such as electronic, cyber, and information warfare, have already become prevalent. Industry 4.0 is a suite of technologies which include robotics, AI, swarms, autonomous weapons, smart factories making bespoke products, big data, and Internet of Things. This is not an exhaustive list, but it's just an attempt to give a flavor of what we are going to be talking about. Aviation industry and its operations have a number of automation applications which will transform operations and maintenance with great improvements in availability and profitability for organizations. I'll cover this happy part in the first of the series of presentations on the subject. Thereafter, I will cover the impact on equipment profiles of armed forces based on trends in modern conflicts. I hope these thoughts would not only help industry plan for future projects, but also the highly regimented mind of the military man to augment their conventional inventories, such as manned tanks, artillery pieces, fighter aircraft, frigates, and submarines with these technologies. The decoupling from the labor arbitrage of developing nations is a strategic direction developed economies have chosen in their technological development. The dwindling birth rates have added to their concerns that foreign sweatshops are not a solution to retain dominance, as eventually they really benefit the local economy. The focus has shifted enormously to robotics, automation, swarms, artificial intelligence, machine learning, quantum computing, artificial wombs, gene editing, biological implants, etc., etc. This renewed focus indicates not just decoupling from labor arbitrage of developing nations, but also there is no more the need for young and large populations for economic growth. We normally think of factories as assembly lines that churn out large volumes of same goods. It is not unusual for distributors to demand a minimum order quantity and volumes for economic viability. In Germany, a car factory has been designed entirely using collaborative robots that make bespoke cars. In this factory, the swarm of robots are just given the design of the car and they collaborate with each other to make the car. The design is digitally engineered to be unique and no two cars are similar. This is not science fiction, but a real factory that's economically viable and in great demand. Think of the possibilities. The defense spares business is notoriously low volume, high variety, and very quality sensitive. Let's assume that we have a geometric LiDAR and a radio frequency instrument that can reverse engineer the dimensional engineering drawing and the metallic properties in a manner that it can be reproduced by a 3D printer. This capability will crack the triple challenge of volume, variety, and quality sensitivity to a large extent, isn't it? Such instruments are now readily available. We now even have 3D printers which can take multiple powders, wires, gimbaled beds, etc. These 3D printers can produce a part with directional hardening in exactly the same alloy and microstructure of the original part. Aviation maintenance organizations should engage R&D to stabilize these processes and digitize these parts for starters, for a proof of concept to realize the power of this technology. Parts can also be remotely printed, reducing supply chain friction and improving availability of hardware at remote locations. Parts auto-aliasing is a very interesting application. Many organizations have facial recognition systems based on security layer at the entrance. The system learns your face from key measurements and can recognize you with a cap, without a cap, with different caps, or with glasses, different angles of your face, etc. This technology is readily available. It can scan thousands of digital drawings and automatically alias parts for inventory optimization and save billions of dollars for a big aviation operator. This can replace the present practice of identifying aliases through part and stock numbers. The manual system is so messed up that we have allocated multiple stock numbers to the same parts and surprisingly the same stock numbers to multiple parts. We can obviate this mess with image recognition technologies which use artificial intelligence and machine learning. Automated inspections of aircraft on the flight line is another very interesting application of these new technologies. These technologies can be applied for automated inspections of equipment that are not wired with sensors and do not have a means of self-diagnosis and communicate with a digital twin, etc. It's a very simple solution. Let's imagine an array of cameras at each gate or shelter looking at a parked aircraft, or a drone looking at a parked aircraft. An AI system can tell if the airframe is fit to fly as much as a human who eyeballs it in the name of doing an airframe daily inspection. Ball or snake robots can be trained to inspect aero engine faces or exhaust areas, and the AI system can tell us whether the engine is fit to fly as much as a human who eyeballs the compressor or exhaust area before declaring an aero engine fit to fly in the name of doing an aero engine daily inspection. A technician could also be given smart glasses for the AI system to communicate an anomaly that would like a human expert to look at. This way we could use a technician with limited training, typically 4 to 5 months, to legally clear an expensive aircraft for flight. Operating level maintenance automation has many more applications. Cameras can be permanently mounted on hanger frames, and deeper airframe inspections can be carried out with a continuous record of faults. Replenishments of fuel and even weapons for military operations can be achieved through robotic replenishment systems and AI-enabled mules. These mules can ferry fuel and weapons from storage areas to forward supply points of operating areas traversing difficult terrain conditions. Self-driving technologies will be a game changer for logistics. We can have an AI-enabled mule for ferrying heavy parts from storage areas to operating areas without human assistance 24/7. Flying an unmanned support drone or a helicopter would be much easier than a self-driving car, and we could see ubiquitous use of these as many of the online retailers are already doing. Warehouse maintenance through robots doing both stacking and picking roles can become common even in the military. One of the main challenges in aviation is to estimate the life of a part, assembly, or for that matter, an entire aero engine or aircraft. Most aircraft already have extensive health measurement instrumentation and generate a significant amount of data in each sortie. This data is presently used to observe if there is a latent failure. Sometimes it is also possible to identify deterioration in performance of individual pieces, anticipate failures, and engage in predictive maintenance, which is bespoke for that particular engine or for that particular airframe. Performance issues can be addressed across the fleet through predictive maintenance schedules of the fleet. Bespoke maintenance for a particular aircraft or aero engine also becomes a possibility. Avoiding over-maintenance due to conservative preventive maintenance schedules will immediately result in improvements in reliability and availability of aircraft. Computers can now self-learn from data lake fed live with non-intrusive instrumentation on the aircraft or the aero engine. Computers can now develop a digital twin of the aero engine, aircraft, and provide a bespoke maintenance plan for each piece. Swarm technologies. The aviation industry is heavily dependent on tug drivers for positioning of aircraft at gates, hangars, and at the operational level. The cost of a trained tow truck driver can be prohibitive and will only keep increasing. The aviation industry has moved on for some time now with tow barless tow tugs, which are controlled by a human. With self-driving technologies that have matured, it is definitely possible to make a tow tug that can follow a human and ensure that collisions are avoided by LiDAR sensors, camera arrays, etc. With swarm technologies maturing, it is possible for multiple autonomous tow tugs to collaboratively tow aircraft and position them with a general instruction on the positioning of all aircraft. Reversing an aircraft is a breeze for these technologies. The tugs would go automatically to their charging stations, much like the autonomous vacuum cleaners that have become commonplace at homes. In this first part of a series of presentations, we have seen the applications of IR 4.0 tech to aviation maintenance and operations, ground operations. We will progressively examine the impact on warfare and consequent impact on equipment profiles of armed forces in the subsequent parts. Thank you for watching and